Welcome back. Let's continue with our discussion of reductions, hydride reductions, in particular now the ones that will produce secondary alcohols. Unlike the previous video where we saw three different ways, I guess four technically, of making the primary alcohols, in order to make secondary alcohols using hydridic reagents, the only real way to do that is to start with a ketone. Because you do need to have a carbon and a second carbon bound to the carbonyl in order to produce a secondary carbon, because all we're going to add to this thing is a hydride or a hydrogen atom, right? So this is really the only way to make it happen. So in comparison to what we saw in the previous video, this is going to seem like peanuts, right? All right, so here we go. We could even use a mild reagent, lithium borohydride, and that will attack the carbonyl carbon, which will force that CO double bond to be broken and have two of those electrons moved over to the oxygen. This will in turn produce a lithium alkoxide, which now possesses that hydrogen there, right? Which makes this a secondary alkoxide. And then the second step is, as you might have guessed it, protonation. Nothing more than that. You quench the reaction by adding water and you produce your alcohol in addition to lithium hydroxide. All right, now in terms of the transition states, it's literally identical to what we saw with the aldehydes. This time around, however, we're just using a ketone, right? So the ketone just positions itself either behind or in front of the borohydride reagent. One of those BH bonds is positioned very close to the carbonyl carbon, and the sodium is interacting with both borohydride and oxygen in anticipation for oxygen turning into a negative ion. And once the hydride is delivered to that carbonyl, that's when we form the alkoxide. And the sodium was already there waiting for this to happen. So there really wasn't any crazy rearrangement. Something that in the mechanisms would kind of make us look like, okay, all this stuff is happening. But no, these things were there from the beginning. Yeah, that's just kind of the way nature does things. It looks for the least troublesome way of making something happen. And well, that's what this is, right? So at the end, you add your water and you protonate it, and boom, game over. You got your secondary alcohol. And this need not be done with sodium borohydride. You could also use lithium aluminum hydride to carry the same process forward, right? In fact, the mechanism is identical to the one with sodium borohydride. The only difference is that instead of this being a boron, it's aluminum. And instead of that being sodium, it's lithium. But yeah, the hydride attacks the carbonyl bond is broken, you form your lithium alkoxide, you now have that CH bond present. Then the lithium alkoxide reacts with water to produce alcohol and lithium hydroxide. So mechanisms identical, doesn't matter which reagent you use, but be aware that sodium borohydride, although it can reduce ketones and aldehydes, it cannot reduce esters, it cannot reduce carboxylic acids, it cannot reduce even amides. So when you're presented with those situations, especially if your molecule possesses multiple functional groups, like it might possess a ketone and it might also possess an ester, if all you want to do is turn the ketone into an alcohol but you want to leave the ester intact, then you want to use sodium borohydride. Whereas if you're trying to turn every single carbonyl compound into an alcohol, then you better use lithium aluminum hydride. All right, and yes, transition state, same idea. Hydride bond position next to that carbonyl carbon. Oxygen is already interacting with lithium. So yeah, same idea. Nothing different right there. Okay, so that's actually it for the secondary alcohols. There's really, like I said at the beginning, there's almost nothing to it. You start with a ketone, you produce your secondary alcohol, as long as you treat it with a hydride reducing agent. All right, now aldehydes. How do we make aldehydes? Because after all, the aldehydes are kind of the midway point between your carboxylic acids, your esters, your acyl chlorides, and the primary alcohol. So this brings us back to the discussion of the reducing agents, the aluminum hydride reducing agents that have a lot of bulkiness around it, right? So we have three TB toxic groups around the aluminum. Over here we have two isobutyl groups in association with the one aluminum hydrogen bond. So the way this basically works is that if you're dealing with the acyl chloride, which is basically this carbonyl compound where X is a chlorine atom, that's your acyl chloride. If you react that with lithium aluminum tri-TB toxic hydride at low temperatures, and I'm talking like -60, -68 degrees Celsius, then you can actually stop midway through the reduction. You can take the acyl chloride and turn it into an aldehyde. And with lithium aluminum hydride, regular aluminum hydride, this will not be possible. Even though you will form the aldehyde, that aldehyde will already be reacting to give you the primary alcohol. But when you introduce these bulky groups, you make it less likely for the aldehyde to be reduced to the primary alcohol. So you stop at that point. All right, but then this is the caveat. The reaction does need to be done under cryogenic temperatures, because if you do not do that, and you have a hot enough temperature, like even 0 degrees Celsius is probably going to be too hot for this reaction to be okay. Even though this is bulky, this will still reduce your compounds all the way to the primary alcohol if you're starting with the acyl chloride. And same thing, your ketone can react with this thing if the temperature is above 0 degrees Celsius. So this needs to be done at low temperatures. Now, in the case of DIBAL once more needs to be reacted at low temperatures, so -60 degrees, roughly speaking, -70 perhaps. But this time you'll react it with an ester instead of the acyl chloride. So if you do this with an ester, you can turn the ester into an aldehyde. And that's actually kind of a nice little segue to make this happen. But like the previous reagent, this one also follows the same trend, that if you do this at higher than 0 degrees Celsius, you will ultimately reduce the aldehyde to the primary alcohol, or even the ketone to a secondary alcohol. So this needs to be done at low temperature as well. So the bulkiness is just part of the contribution. And the reason why you need the bulkiness, and on top of that you need to keep this under low temperatures, because when you think about the reaction coordinate transition diagram, here's your acyl chloride, for instance, or it could be your ester. This is going to have an activation energy to react, and the substance, specifically the acyl chloride, that's pretty reactive. So the activation energy is not that high to begin with, right? So here you can use those bulky reagents, and these two guys will react because the activation energy is not that big to begin with, right? Is this thing right here. That will produce your aldehyde, which is a relatively more stable molecule. Now, if you do this at low temperature, notice that the activation energy to go backwards to the reactant stage, now this is going to be very unlikely to happen, because the activation energy to go backwards is a lot larger than the activation energy to go forwards tends to be. At the same time, by introducing this bulkiness to the groups and having this at low temperature, it prevents the reaction going further than the aldehyde stage, because in order for this to happen, now you have to go through an activation energy that is not as large as the backwards activation energy for the first step, but it's definitely larger than the first activation energy. And so you basically trap the molecule. Instead of going all the way to the alcohol, you really can't make that trip. You're basically stuck at the aldehyde stage if you do this at low temperature in combination with the bulky aluminum hydride counterparts. All right, so that's the whole idea. We're basically counting on kinetic stabilization to stop at the aldehyde stage. We're making it kind of impossible for these guys to reach out to the aldehyde and react with it because of the bulkiness and because of the low temperature. All right, so now what I'm going to show you is a nice little sequence that kind of encompasses the different changes you can make and how you can go to those aldehydes ultimately. Because you could start with a carboxylic acid. Now the carboxylic acid is not going to play out with either of the two reagents I just mentioned, but a carboxylic acid can be turned into an ester if you react the carboxylic acid with a corresponding alcohol under acidic conditions. This will impart that RO group onto the carbonyl, making an ester. And you will learn this type of reactions in detail in the second semester organic chemistry class that you'll take in the future. Also, and alternatively, the carboxylic acid can be treated with a very different reagent. This is known as thionyl chloride. And thionyl chloride basically exchanges oxygen for chlorine. Basically takes one of the oxygens out of the carboxylic acid and it yields a chlorine instead. So you end up forming your acyl chloride that way. And once more, this is a reaction that you will learn in detail in the second semester part of organic chemistry. Right here, I just want to kind of show you this for just to add context to the process. So if you were actually dealing with a carboxylic acid, there are ways to turn them into esters or acyl chlorides before you can turn them, or before you decide to turn them into aldehydes. Oh, and one more thing I should tell you is that the acyl chloride can easily be transformed into an ester by reacting it just with alcohol. You don't need to have it under acidic conditions. In fact, this thing right here is pretty acidic as is. So these are the different ways in which you can transform into the different components. So once you have that ester from your carboxylic acid, you can lower the temperature to -78 degrees Celsius, easily done with an acetone dry ice bath. And then you can add to this thing DIBAL. And under those conditions, you will turn the ester into an aldehyde. Alternatively, you could treat by the way, you could treat the carboxylic acid with lithium aluminum hydride. That will take you directly to the primary alcohol, right? Which might not be what you want if you are looking for the aldehyde in particular. Now, the other option, of course, is to take your acyl chloride, lower the temperature to -78 degrees Celsius, and react it with lithium tributyroxy aluminum hydride in order to form the corresponding aldehyde. The last thing I want to kind of mention, just to kind of complete the sequence, is that if you do raise the temperature, before you quench the reaction, then you will basically get those aldehydes destroyed and turn into the primary alcohol, because every aluminum hydride reducing agent above 0 degrees Celsius is going to yield the primary alcohol. So just keep that in mind. That's an important point to be made. Okay, so the last thing I just want to mention to give you some more context is how exactly do these reagents happen to work with the specific ester or the specific acyl chloride to form the aldehyde. And I'm going to start first with DIBAL. Now, if you think about this, DIBAL is nothing more than electron deficient aluminum. In fact, that's why you have this funky looking type of bond. This is what we call a 3-center or a 3-center 2-electron bond. So you're not actually violating the maximum amount of electrons that a hydrogen could have. In fact, you should not be thinking of those bonds as having 2 electrons each. But this is more of a topic of inorganic chemistry than it is of organics. So I don't want you to dwell too much on that. But the thing is that if you break this in half, because after all this is a dimer, all you have is 2 isobutyl groups and 1 hydrogen bound to any one of the aluminums, and that means that the aluminum is electron deficient. So here's where the ester comes in. That oxygen bond can actually interact with the aluminum to complete its octet, and because of that interaction, now you bring that hydride close by to the carbonyl carbon to perform the reduction. And this is how that happens. Now, by the time the reduction takes place and you form the aldehyde, the reason why the aldehyde doesn't react further to give you the primary alcohol, at least under low temperatures, is because you've lost that interaction. This interaction came from that oxygen exclusively, and you no longer have that oxygen present. So the aluminum is no longer able to kind of easily, meander nearby the carbonyl carbon. and that's what makes this reaction stall at that particular stage. So it's actually kind of an interesting structural feature. All right, so it's all about that interaction. You know, once you make the aldehyde, the interaction is no longer there, so you no longer have the reaction going forward. And for the acyl chloride, the story is a little bit different, because if you look at this thing, you can say, well, what the heck? This is even bigger than DIBAL, you know, like, and it's got a lot more bulk associated with it. So how could you even approach the chlorine atom that's even bigger than oxygen? Well, the reason this is true, or the reason this reaction even happens, is not so much because of the size of what's bound to the carbonyl, but because if you think about it, that carbon-chlorine bond, that's a weak bond. In fact, chlorine, as you already know from the substitution chapters, is a good leaving group. In fact, there is an equilibrium between the acyl chloride, as you can see here. If the electrons of that oxygen come down here, we can kick away the chlorine as a leaving group, and we end up forming this particular oxonium cation, also known as well, let's go with oxonium cation. I don't want to confuse you too much, but you have a small amount of this that gets formed in solution, and it's in equilibrium with that. Okay, these are not resonance structures, by the way, because we have broken that connection, but we do have a small amount of it. And when you think of it that way, you realize, well, wait a minute, that carbon no longer has a third thing bound to it. It's basically linear, and this is the most accessible that you could ever place a carbon from the point of view of a nucleophile, or in this case a reducing agent. So the fact that this is pretty bulky prevents it from reacting with esters or other carbonyl compounds, but not with one that is already got a linear shape. So that will make it very likely for it to interact, form your aldehyde. But then your aldehyde never has the chance to ever form this linear carbo, or well, this linear cation. And because of that, you stall once more at the aldehyde stage, so long as the temperature is cold. Okay, so that concludes the hydride lectures. In the next set of videos, we're going to talk about how we can still perform reductions, but this time, instead of introducing hydrogens to what used to be the carbonyl carbon, rather introduce other carbons to it. Okay, so I'll see you in the next video.